Before we consider uniform circular motion, I first want you to consider the following projectile problem. What we have right here is a little toy monkey, and we have a little launcher right here, and the launcher is aimed directly at the monkey. The launcher will project the ball, and at the instant the ball leaves the launcher right here, the monkey, which is suspended by a magnet, will be released and it will fall. Question is, what will happen? Will the ball hit the monkey? Will the ball completely miss the monkey? Or will the ball hit the monkey only if it has a very high velocity? And clearly we're going to assume that the ball will in fact reach the monkey. So, enter your answer in the box that appears, and then we'll look at the answer. We're going to look at the answer by considering a video where they actually do something very close to this, except rather than a toy monkey, we're going to have a ball right here and launch a second ball at it.
The target ball is suspended from an electromagnet high above the floor. The projectile is aimed at the initial position of the target. The balls hit each other. If the speed of the projectile is increased, the hit occurs at a higher location.
So note that the only assumption we have to make is that the ball, in fact, has enough initial velocity to reach the target. So long as that happens, they will collide. The ball moves faster, the collision will simply occur higher. The reason for that is both the launched ball and the target ball are falling under the influence of the exact same gravity. So they're moving down at the exact same rate, and therefore they collide. Now, what we're going to consider now is an object moving around in what is called uniform circular motion. Circular motion simply means it's going to be going around in a circle. The uniform part means it'll be at a constant speed. That means it will not be accelerating in the sense of speeding up or slowing down, but it will be accelerating in the sense that its direction will be changing. And that is also acceleration. So what we're going to do is calculate the rate of acceleration of an object that is moving at a constant speed but constantly changing direction. We're going to do that by just using the definition of acceleration as the change in velocity. And we will have to consider the velocity as a vector because it's the direction that will be changing. We'll represent this by having an object at point P, and it'll be moving around in a circle at a constant velocity. It'll be going from A to P to B at a constant speed. So the magnitude of the velocity at point A will equal the magnitude of the velocity at point B, and we're just going to call that V. And what we want to do is find the acceleration at the midpoint P. A will be an angle theta before it reaches P. B will be an angle theta afterwards. And to get the acceleration at P, what we're going to do is let the angle theta get arbitrarily small. Now, in order to figure out the geometry of this, we're first just going to consider a simplification of this setup. All I've done is eliminate the circles and the labeling for the velocity vectors. What we have right here, this is the center of the circle. This right here is point A. This is the angle theta. Notice I've labeled this also as the angle theta. So what I want to show is why that is true. Notice this as the angle from the velocity, which is tangent to the path. So it's tangent to the circle, which means it's perpendicular to this radius vector. This right here is a radius vector. So this right here will be a right angle. In addition, because this right here is the x direction, parallel to the x-axis, and this is the y-axis, this right here will also be a right angle. What that means is that this angle theta and this angle, which I've called phi, will in fact be complements of each other. They will add up to 90 degrees because some of the angles in this triangle must be 180. We've already got a 90-degree angle right here. But this angle is also the complement of that angle right here because they're both opposite sides of a right triangle. So this angle is the complement of the same angle to which this is a complement of. Therefore, these two angles, since they're complements of the same angle, must be equal. So this angle up here is also theta, and we're going to rely on that. So let's go back to our diagram. We've just shown that this angle must equal that angle. Now, what we're going to do is calculate the acceleration at point P as being the change in velocity, which is the final velocity minus the initial velocity, divided by the time it takes the object to go from A to B. So this is the problem we're going to consider, is the acceleration is the change in velocity divided by the change in time. We're going to calculate this by considering each of the components of the acceleration separately. So the first thing we're going to look at is the x component of the acceleration, and that'll be the change in the x components divided by the time. However, notice the x component at A is just v times the cosine of theta. The x component at B is just v times the cosine of theta. And in the x direction, the velocity doesn't change. It's going to the right at A, it's going to the right at B, and at the same rate. So the acceleration in the x direction will be 0. There is neither a change in direction nor a change in magnitude. Now we're going to consider the y direction. At A, it is going in the upward direction, and this y component of the velocity will be v times the sine of theta. But at B, on the opposite side of the circle, the final velocity, it'll be going down at the same rate. So at this point, the y component will be minus v times the sine of theta. So this is the velocity at A, here's the velocity at B. The change in velocity is the final velocity, which is this, minus the initial velocity, which is that. And in this case, they're going in opposite directions, so they don't cancel out. So the change in velocity is minus 2v sine theta. Now we have to figure out what is the time. Well, it's the time for it to go from A to B, and it's moving at a constant rate. So it is this distance, this arc length right here, divided by the speed v. Well, the arc length right here will just be r times this angle, and this angle is just 2 theta. So the distance that it's going to travel, d, is r times 2 theta, divided by the speed v. I'm going to take this and divide it into that. So we have minus 2v sine theta, divided by 2r theta, divided by v. And we're just going to simplify that. We take the minus sign out. We've got a v and a v here. We collect them together. It's v squared divided by r. The 2's cancel out. And then right here we have the sine theta divided by theta. And we're almost done. What we now want to do is let theta become very small. So basically we want point A to be right before point P and point B to be right afterwards, which means theta will be arbitrarily small. We can see what happens to the ratio of the sine of theta divided by theta as theta gets small by graphing it. So right here I've looked at the sine of x divided by x, and on the horizontal axis right here I have x, and on the vertical axis I have the sine of x divided by x in radians. And notice the scale right here is fairly small. We're only going from 1/10 of a radian down to 0. And the scale here is 0.9982 up to 1.0002. So this is very much blown up right around 1. And the ratio of the sine of x divided by x essentially goes to 1 as theta or x goes to 0. So as we let the 2 points A and B converge on the center point P, this ratio right here goes to 1. And we end up with the acceleration has no x component. It does have a y component, and its magnitude is v squared over r. We're going to replace the minus sign with a subscript c. C stands for centripetal. Centripetal means center-seeking. So this is an acceleration that's towards the center, because that's what the minus sign right here, when we're at the top of the circle right here, downward actually points towards the center of the circle. So this acceleration is towards the center, and its magnitude is v squared over r. So this is what our result is. At point P, the acceleration is a centripetal one. It's straight down, and its magnitude is v squared over r. But note, this is a circle. There is nothing special about point P. We could have done it around another point, which we could call Q, down over here. We would have gotten the exact same result, because all we would have done was take our axes, rather than using the one we have right here, we'd simply tilt them so that the axes were through point Q. Then we might have to tilt our head, but we'd have the exact same problem. We would still end up with an acceleration that's pointing down the negative y-axis towards the center of the circle. It would have had the exact same magnitude, and it has to because all the points on the circle are identical and completely indistinguishable. Now, one point of confusion is that we've just derived a different set of kinematics. We've already done the linear kinematics, where we've got these equations, which we derived, but that is derived under the assumption of an object moving in a straight line at a constant acceleration. These are not fundamental equations. These kinematics equations come from an assumption that an object is doing something like this, speeding up while going in a straight line. We now have a completely different type of motion with different types of assumptions. Here we've assumed we're moving in a circle, so r is constant. We've assumed that we're moving at a constant velocity, and we have now calculated what the acceleration is. So we have to, when we do a kinematics problem, ask ourselves, what kind of motion are we describing? Are we describing linear motion or circular motion? And use the correct kinematics equations. Now let's consider a simple example. Here we're going to have a car going around a circle, and it has a radius of 400 feet, and it's moving at a constant 45 miles an hour. I want you to find its acceleration in meters per second squared. Write your answer in the box that will appear, and then we'll go over the solution. Okay, first thing you need to do is convert everything to metric units, because I want the acceleration in meters per second squared. I gave you the velocity in miles per hour and the radius in feet. So 45 miles per hour, we converted as 20.1 meters per second, and 400 feet corresponds to 121.9 meters. We take these, we plug it into our centripetal acceleration formula, and we get 3.32 meters per second squared, which is our answer. Notice when you get an answer like this, you should always immediately in your mind compare it to g, because that's an acceleration we're familiar with. And notice it is about a third of a g, which should make sense. It's a reasonable acceleration. You're going reasonably fast around a curve. You would probably feel that. It wouldn't be horrible. It's not like you're going around at 10 g's or anything. You're only going around at a fraction of a g. If you got an answer that was, say, 33.2, you might ask yourselves, did you convert the units correctly? Did you remember to square everything? Did you divide correctly? Because the answer, when you're driving in a car and 45 miles an hour is a reasonable speed, the result acceleration should be reasonable.